Good afternoon. Welcome to my talk on operator overloading. A little bit of history, a lot of principles, some practice. I wanted to do a talk on operator overloading because it seemed to me a particularly unloved part of C++. I'm sensing that in the crowd. So here's what I won't be talking about, because it could cover a lot of things. So I'm pretty much going to be talking about why we should embrace operator overloading and why we should do it with the sort of the regular operators that we think of when we think of operators. So the arithmetic operators, the bitwise operators, equality operators. You know, a lot of things fall into the category of operators in C++. I'm not going to be talking about the kind of esoteric things. So operator overloading is unloved. And it's because it's just not that good in C++. Operators in C++ were fixed to a large extent in about 1969 when Ken Thompson invented B. Things we can't control include the names of operators. We have a fixed syntactic set. We don't get to introduce new operators. For example, a power operator might be nice, but we can't do that. We get fixed precedents, and that often gives us a very short list of operators to choose from if we want to overload. Sometimes associativity is a problem, and we'll come to that. We don't get any choice in arity. You might think that's a strange thing to want to vary. If you read Ken Iverson's Turing Award lecture of 1979 all about APL, that might change your mind about wanting to overload arity in operators or change arity. We don't get a choice of whether to make operators infix, prefix, or postfix. And we don't get a choice over evaluation semantics. Some operators short circuit. We don't get to control that. But in theory, all of these things are rules that the compiler knows. It's just that they aren't exposed to us in the language. OK, so why do we care about operators? And what can we do with the power that we do have? The obvious first question is, why should we use operators at all? Why should we prefer them over named functions for certain use cases? So if I were to ask you why, you might say, well, they offer a concision. They allow us to express our code concisely. Sometimes, some people might say for performance, maybe, or it may be something we think about. Take advantage of ADL, maybe, because we can, or sometimes because we have to. If we're putting things in a set, for example, we require things to have ordering or equality for other uses. So for some or all these reasons, maybe. But one big reason, I think, is because when we use an operator, it conveys meaning about our types that named functions can't. So a grade school child can intuit properties of addition, right? Before we know the names of these properties, before we know about commutativity and associativity and what to call these things, we can intuit these things when we're 6 or 7, and we learn this notation to go with it. So when we use operators in C++, it tells our users, it taps into this intuition that we have. And addition is perhaps the canonical operator for this reason. So saying that another way, as it's been said by Biana, it's probably wise to mimic primarily conventional use. So that raises the question, what is conventional, right? If we'd better be conventional, what is conventional? The counterpoint to sticking to convention is conventions change. Sometimes convention means just what I'm used to. It might mean the only thing I've experienced. So how many of you recognize this item? Probably a lot of people. OK, so this is the Canon Digital Ixus, or the ELF, I think it was called in the US. It's 18 years old, Wikipedia tells me, so it's an adult this year. It was a really good point-and-shoot digital camera, right? But even today, when I say to you it's a digital camera, that's kind of an anachronism, because what cameras aren't digital now? Really high-end professional photographers use film cameras, but they also use digital. The only reason to have a camera like this today, when we all have a camera in our pocket anyway, is that you want to save your phone battery. So conventions change. Here's another good example of a changed convention. So what we think of as kind of, Marshall, you have one. What we think of as axiomatic, i.e. mathematical notation, actually has changed a fair amount over history, and even recently. These four names in particular are famous for inventing and or popularizing different elements of mathematical notation over the years. Now, you look at this list and you say, well, that's fine, but that's 300 years old or so. Okay, I say. So what's the answer to this? It depends. Okay, so 3. Okay, this is a well-known approximation to pi, right? If we're talking about integers, yes, it's 3. Well, are you sure about that? Because until the turn of the 20th century, this slash symbol, I mean, when we wanted to say division, it was much more common to say a colon. And that notation is still in use today when we talk about ratios. Even today, a mathematician wouldn't normally write this. They'd write a regular, like, two-dimensional fraction. As far as I can tell, using slash for division is probably an artifact of computer terminals. And if I ask you about what these mean, well, they're even more arbitrary, really. They were made up in about late 60s, as I say. So these are only slightly older than me. So yes, we want to be conventional, but convention can change. So where convention exists, and sometimes where it exists outside of mathematics, is an important source for following it. Okay, so some other operator overloading advice we might take from Scott Myers. So Scott Myers said in his book, More Effective C++, when in doubt, do as the ints do. So this is advice for designing our types. Int is well understood, int is fast. We could perhaps try and find an operator which acts like ints do in the sense of being canonical. So I might ask the question, how about we look at when in doubt, do what operator plus does? Let's try and find the most normal operator in the sense and see if we can devise some guidelines for overloading it. So I want to ask you, what are some properties of plus in mathematics? It's commutative. It's associative. It's closed. And somebody said it has a 0. Right. It's closed. It's associative. It's commutative. It has an identity. We'd call it a monoid, right? So now in C++, do we have those same properties? If we're talking about closedness, I mean, so for unsigned ints, maybe all these things. But that's not typically how we think of addition. Okay, so we've got overflow, so it's not really closed. Is it associative? Not always, right? Is it commutative? Again, no. Does it have an identity at least? I would say yes. Sometimes it has more than one. So we try to follow mathematical conventions, but they're not always what we want to stick to dogmatically. So operators are important, though. So in 1956, the IT compiler, the internal translator, was a compiler for the IBM 650. And it was perhaps the first compiler that we would recognize as a compiler in the modern sense, i.e. translating human-readable code into machine code. Prior to that, there had been sort of translators and things. But this was the first sort of thing we'd recognize as a modern compiler. But it had one downfall. It didn't have operator precedence as we know it today. And as a result of that, it was very difficult to use for programmers. The lack of operator precedence was the single greatest cause of errors. So I think this tells us something about how operators convey meaning. So I hope I've given a pretty good answer as to why we should use operators. They convey meaning not just about the operations in the way that function names do, but about the types that we act upon. And because well-used operators allow readability through concision, and because operators are at the heart of expressions, and expressions allow manipulation to give us better readability and perhaps better performance. All right, so that's kind of a motivation. Now, if we're talking about mathematical principles, they're not all created equal. Which one should we follow? And I sort of thought about this, and I have a selection of principles in order of importance approximately that I think are important to follow. The first one is this. If you break the oppositeness of equality and inequality, you certainly wouldn't pass a code review from me, and I would hope from your peers. So equality had better mean the opposite of inequality. Another very important one, actually, is associativity. Most of the things we do, most of the types we use, most of the operations we use are associative. And associativity is one of the key properties that allows us to manipulate expressions. Now, unfortunately, in C++, we don't yet have the machinery to take advantage, really, of associativity fully. I'll come to that in a couple of slides' time. This is kind of an important one if you can provide it. The law of the excluded middle. This makes thinking about ordering a whole lot easier. So either a proposition is true or its inverse is true. And this is mostly true, notably not for float. We'll come back to that in a bit. But if you can provide this guarantee, it makes thinking about ordering a lot more easy, and it makes writing your less than operators kind of easier to think about. And then we get onto the nice to haves. So commutativity of plus is actually really nice to have. And it's probably too late to fix stood string now. Also, stood reduce is sort of annoying to me because it requires commutativity, where mathematically it might only require associativity. I understand that it requires commutativity for efficient implementation and vectorization, but it's sort of unfortunate that reduce requires commutativity. Bryce?
It's just undefined.
Okay, all right. Apparently, it doesn't require commutativity if you're prepared to live with undefined behavior. All right. But I would like us, Bryce, to get something in the standard that only requires associativity in a reduce-like algorithm. How about accumulate? Yes, but accumulate gives you the strict linear. Like, the point of associativity is to be able to group terms.
Gotta make tough choices in that.
You do have to make tough choices. All right, well, I won't get everything I want. Okay, here's another nice to have. A distributive law, right? This is something we learn in middle school or something like that. I didn't go to school in the US, so but anyway, we learn it in school. This is something that allows us to manipulate expressions. And these properties, these last two properties I mentioned, allude to a mathematical structure called a ring. We could also cite, where plus and multiplication form a ring, and an XOR also form a ring. There are lots of things in mathematics that do this. And we can think about things like De Morgan's laws and manipulations of expressions, identities that we know from school. If we make our types and our operators adhere to this kind of structure, it gives our users the ability to apply those things that they already know. So it behooves us to follow user expectations in designing our operators. Now, this one more thing I have here is it's nice to have closedness. But to me, this is an interesting sort of lever, an interesting choice to make over your types and your operators. The important thing is to know whether or not you have closure over your type. So, in C++, even a division operator is closed over integral types, which is a little strange, but mathematically speaking. But when we relax this rule of closeness, it can lead to good design if we divide our types. And that leads me to talking about affine spaces. So an affine space is basically a vector space where a distinction is made between a point type, a position, and a vector type, or a translation. And it's quite possible, even likely, that in a given vector space, those two things could be representationally the same. And it's likely, although it's not required for affine spaces, that your space has an origin. So although the things are representationally the same, vectors and points, if we make them different types, that leads us down an interesting path as designers of operators and designers of types. So affine spaces are types and operators working together as a team. You have, as I've said, points are type 1, vectors are type 2, and then you have operations that relate vectors to each other and relate points to vectors. And there's no need for an origin. Now, there's a couple of good examples of affine spaces in the standard. The one I really like is chrono, time point, and duration. Now, it's only a one-dimensional affine space, but it's still an affine space. And by looking at it that way, it helps us define the space of operations that we can use and the ones that make sense. So Chrono defines these operations. It might define a few more, but slideware. So we know that addition and subtraction, therefore, is closed over vectors, i.e. durations. And we know that when we take away one point from another, we get a vector, a duration. But we can also think about scaling vectors. That's why we have the operator star and operator slash. Since we're in a one-dimensional affine space, it makes sense to have a modulus operation, dividing one duration by another. If we were in a two-dimensional affine space, it might make sense to have a dot product. We could think about, when we think about things in affine space terms, we get to leverage all of the knowledge of mathematics to sort of help us flesh out the design space of our types and our operations. And that's really useful. So, in answer to the question, why should we overload conventionally? Because it helps users with intuition, manipulation, and properties of types, but also because it helps us as type designers and implementers. It helps us identify what is a complete basis for our type, what is minimality versus convenience functions, which functions are likely to be efficient or otherwise, and in general, it helps us explore the type and operation space that we're going for. Now, the other reason to be conventional is, of course, it helps our users leverage the compositionality aspects that are built into the language and the library in terms of stood accumulate and reduce in the library and all of the, I forget all of the names of the algorithms, like the reduction type algorithms. There are 4 or 5 of them, I think. And, of course, in the language in CppCon, we got fold expressions. So let's talk a little bit about what came new in CppCon and how that influences what we might do with operators. So fold expressions fold or reduce a parameter pack over a binary operator. This is a binary left fold, and it acts like it's left associative. So things are grouping to the left, which is sort of obvious if you look at this example, because cout, the type of cout is such that this can only group to the left, right? Most of the operators we use are left associative, things like plus, multiply. And so most of the time, if you don't care, if it's not important to you, this left to right grouping is just fine. But if you have an operator which is not commutative, fold expressions become even more important. If you have, let's say, matrix multiply, because fold expressions allow you to choose left fold or right fold. And if you have an expression which is not commutative, that becomes an important choice. The operation is usually associative, so it doesn't matter which way the pack is folded, except in that application to the initial argument. Now, so if you have a non-commutative operation, fold expressions are easy. You can write them either one way around or the other way around. Accumulate is much less easy to write. I think I have that in a couple of slides. Talking about fold expressions, I just wanted to touch on unary fold expressions. They are defined for logical and logical or and comma. I'm going to tell you you shouldn't probably still overload those operators because. So what happened was with CppCon we got these evaluation order guarantees. with P0145. And it changed things slightly for these three operators. So prior to C++17, if you overload, let's say, logical AND, you don't get the sequencing of evaluation, and you don't get the short circuiting. After C++17, you do get the sequencing, but you still don't get the short circuiting. So I would still stay away from overloading these operators. But they are really, so in C++17, to recap, associativity, really important for fold expressions. If you have a non-commutative operator, even more important, or a non-commutative function, overloading an operator for it allows you to use fold expressions. And you probably still don't want to mess with those other operators. So just to kind of drive home the point about if you have non-commutativity, to use accumulate is a pain to make it do a WriteFold. You have to do something like this. So I have this write multiplies struct. Note that the order of operands to that is flipped around on line 4, where I call operation there. And accumulate uses reverse iterators. To write this, and this isn't even fully generic, but to write this in a generic way to apply something on the right is, as you can see, a lot more work than doing just a WriteFold with a fold operator. This is much nicer, much clearer in intent. And your users get this for free without having to jump through the hoops of writing that accumulate WriteFold. So that was kind of what's new in C++17. Let's look a little bit about what's coming in C++20. We got a whole new operator, and it's officially called the three-way comparison operator. And it's colloquially called the Spaceship operator. It's even called that in the standard, expra.spaceship. You probably heard something about it. It's designed to be a three-way comparison on its operands x and y, something like strucump. So informally, it's if x is less than y, return sort of -1. If x is equal to y, return 0. If x is greater than y, return greater than 0. Informally. So I've got a disclaimer for this section. Everything's really new, so new that it's not yet implemented in some cases. So I'm going to try to tell you about what I think I know so far, what I think we know. I've talked to a few people about this. So when you include compare, that's the new header, you get these 5 types. And these types are comparison categories. There's strong equality and weak equality, strong ordering and weak ordering, and partial ordering. So when you overload the Spaceship operator for your type, it returns one of these types, right? And which type it returns depends on what you want for your type. Now, the difference between strong versus weak here is what the standard calls substitutability. And it's the idea that if I have 2 values, x and y, let's say they compare equal. If that's strong equality, then I can't tell the difference between them by anything that their public interface exposes. So strong equality means if x is equal to y, then f of x for some function is equal to f of y. They're substitutable. Weak equality doesn't have that, and similarly for strong ordering and weak ordering, it's the same distinction. And we'll get to partial ordering. So I've got some examples of things that I think could fall into each category to help understand this. Bryce, you're going to...
What if I write the Spaceship operator and I don't include the header?
What if you write the Spaceship operator and you don't include the header?
Am I allowed to return something else from the Spaceship operator, some other thing?
Are you allowed to? I wouldn't recommend it. I would recommend including the header. But you tell me. You probably have more information about this than I do.
Yes, you can use the operator. You can't use any of the types or implemented or grading.
Right. So if you implement the operator and return literally -1, 0, or 1, does that work?
No.
Titus.
It probably doesn't, but it's also the case that if you overload OStream output and have it return an int, it also explodes and you're done. So just don't
Yes. So don't overload operators and have them return things that the standard doesn't cover. So again, the disclaimer on this part, it's very new. The code I'm going to show you in a couple of slides works on like Clang trunk or GCC trunk or something on Godbolt, but sort of partially works. So the idea is that if you provide this operator, you get all of the comparison operators for your type, and that isn't necessarily true of compilers today. All right, so things, and again, these things, I'm going to show you some of them have stood in front of them. These aren't all defined for the standard yet, but these are examples of, just illustrative examples of things I think would fall into each category, just to help you understand the categories. Strong equality, note that we're not talking about ordering yet. Strong equality means I can't tell the difference between two things that are equal. If I have two things that are equal, there's no function I could call on them to distinguish them. So something that might fall into that category is type info. You have two type infos that are equal. If you call functions on them, what you get out should still be equal. It's actually quite hard to find examples of weak equality in the standard, but I think file system path is a candidate. You can think about having a relative path and an absolute path that refer to the same thing, the same object on disk. They're equivalent, but they might not be equal in representation, right? So you might be able to tell the difference between them through their public interfaces, but they are, in some sense, equivalent. And weak equality gives that notion of equivalence. Now, when and if file system path is actually given an operator Spaceship in the standard, I don't know whether it will be weak equivalence or whether we might decide to give it some ordering as well. That's possible. But it's a good illustrative example of weak equivalence. All right, so let's look at ordering. So both strong ordering and weak ordering are examples of a total ordering, which means that exactly one of the following is true. Either A is less than B, A is greater than B, or they're equal. Vector iterators or iterators into a data structure in general are a good example of a strong ordering, which is to say that, remember, the strong property has the substitutability. So you'll always be able to compare vector iterators, let's say. And so notice that there's still a precondition there. They still actually have to be into the same vector. And again, weak ordering is another one of these things where it's actually hard to find types in the standard that might fit into this category. Case-insensitive strings, which admittedly aren't in the standard, but they are a good example of weak ordering, right? Because they would, again, you'd always be able to compare them, greater than, less than, or equal to in some sense, but they wouldn't be strongly equal to each other. Now, when we come to partial ordering, it's the case that none of these things may be true. So that's the difference between total ordering and partial ordering. There are some things which aren't orderable, is what partial ordering says. And the famous example of that is floats, because we have not number. All right, so that's a quick rundown of the Spaceship operator. Remembering all this is new. But I thought, I take this for a spin. I take this for a test drive. Last year's SCM challenge, Manuel is sitting right in the middle here. This was a challenge at last year's CppCon, one of the coding challenges, and it was to write comparison operators for this case-insensitive string class, CI string. And I came up with a solution. Manuel came up with a solution. I think they were pretty much equivalent. Weakly equal. So here's how I solved it, and here's how you might solve it, right? So we need equality and ordering on the case-insensitive string. So prior to C++17 or 20, let's say, we write a case-insensitive comparison functor for equality and one for less than, and we're not dealing with like Unicode characters here, so we're just calling 2 upper. And then we write equality operator and operator less than in terms of that operator, calling stud equal, and then calling stud lexicographical compare. Okay, everyone happy with that? So once we have those 2 operators, then we can implement the rest. And the way they get implemented is pretty much always the same. You can substitute almost any type for CI string here. Once you have that equality and less than, these functions don't change. This is kind of the canonical way to implement the comparison operators. Notice that we never do, we flip around the operands so that we always do exactly one operation here. Sometimes a not, but we basically don't, in particular, to do less than or equal to, we don't do the naive thing of less than or equal to. So this is the sort of canonical and efficient way to implement these operators. They're also free functions, as you can note. And free functions are, in general, a little bit better than member functions. I prefer them because, well, for 2 reasons. One, they increase encapsulation. If you're working in terms of the public interface of your type, that's generally a good thing. The slightly more nuanced reason is that it puts both operands on equal footing, which is somehow easier to think about in terms of the mathematics of it. So, and if you can possibly make the equality operator and the less than operator be free as well, so much the better. Sometimes they need to be friends, but if they can be free, that's great. All right, so that is the pre-C++20 picture. Manuel, I imagine yours looked very similar, yes?
Yeah, I used macro. Because
You used a macro?
Because you also have to do comparison of strings.
Yeah. Okay, so this is a slide where the full thing last year was comparison with const char star and strings and string views and things like that. But basically this is how you do it. So with C++20, what does the spaceship operator give us over how so I should say that in order to do this for const char star string, the amount of code was a lot, and it was all pretty much all boilerplate. As you can see, like I said, these dozen lines, they never change. You can just copy paste your type in there, copy-paste your type, and these never change. So this is boilerplate, and for however many types you need to stamp this out for, you had to do this before C++20. Well, or you could use std relops, but I think there are other reasons. Marshall's saying no. I shouldn't have mentioned that. Strike that from the record, please. Okay, so how does that change with 20? Well, you can write this. So this is operator, spaceship operator, the 3-way comparison operator. It returns a weak ordering, because remember, this is our case-insensitive string. And there's a new algorithm, lexicographical compare 3-way. And what that takes as its comparison, that compares the underlying chars, is itself a 3-way comparison. So if you look at that lambda, we are returning a thing of type std weak ordering. And those are basically enumerations. So we return one of the appropriate enumeration. And with another nod to C++20 here, we don't have to write a functor anymore. We can now pass a lambda in directly because non-capturing lambdas are default constructible in C++20. Everyone good with this slide?
Say that again about default constructor.
So in the previous slide here, I defined functors, struct ci compare equal and ci compare less, with operator paren. Now in C++20, and I passed them in here to the algorithms. In C++20, I can pass a lambda directly to the algorithm, and its type is inferred. Obviously, we can't say the type of the lambda. But the algorithm knows how to, if the lambda doesn't capture anything, in C++20, non-capturing lambdas are now default constructible. So just by knowing the type, the algorithm knows that it can construct one when it needs to.
But that's not what's happening.
You're passing in an instance,
But-
like an actual instance.
You're passing in the decay function pointer. Non-capturing lambdas decay to a function pointer. Yeah.
That's right. Okay, so that's not what's happening here is the comment. Non-capturing lambdas decay to a function pointer. That's true. So, okay. But this doesn't compile prior to C++20.
It should. What wouldn't compile is if you pass only the type directly into the
Own.
parameter list. Decal type of the lambda.
Okay. So I could define the lambda outside the function call and just decal type it as a template parameter, as a template argument.
Yes.
Right. Okay. Sorry, slideware. The point stands, though, that lambdas that don't capture are default constructible in C++20, so you can you can use them much more nicely with things like this. So I ask again, is everyone cool with this approach? Some people say yes. In general, so there's a problem with this slide. The problem is, well, so this absolutely works. This function does everything. I mean, assuming compiler support and everything, this works. The problem is, what if we just wanted to check equality? Well, this function is doing a lot more work than it needs to do to check equality of case-insensitive strings. Because when we called stood equal before, that has like early outs for different length strings and things like that. I don't want to incur a lexicographical compare three-way on two strings where I could just early out if I'm just wanting equality. So yes, this works, but this tells me that library support isn't quite there yet for the spaceship operator. There's no stood equal three-way yet. Now, I could write this function, and I believe that I could also overload my equal operator for this type and get back that performance. I think that's true. But jumping on the bandwagon of the spaceship operator, and this is perfectly like a fair observation because, I mean, C++20 is still 2 years away, right? We've got time to work this out. We're still working on this. But
Couldn't lexicographical compare three-way error out, or not error out, but return early as soon as it discovers one that's not equal?
so the question is, couldn't it return out? It doesn't know whether you wanting to test for equality or less than. It's only saying when you call lexicographical compare three-way, it's giving you back that -1, 0, or 1. It doesn't know whether you actually want 0 or other. It has to give you one of the three, and it has to.
But like StirComp, for instance, can go and say A minus B, A minus B, A minus B, etc., until it finds a difference, or it reaches the end of the string and it was equivalent the entire way, in which case the end is it's equal.
Absolutely, yes. So as soon as there is a difference, it can return, yes. But you don't get the early out behavior that you get with stood equal, where you can very cheaply up front check the length of the strings. They can never be equal if they're different lengths, right? So if all I wanted was equality, I'm leaving performance on the table with lexicographical compare three-way. Marshall? Right, that was the point Marshall was going to make. Okay, so perhaps there's room in the standard for stood equal three-way. And if I wanted, so there is, I know some thoughts going on, some discussion about how to apply the spaceship operator to containers, like string. And maybe we need stood equal three-way. Maybe in the future, when we do have this in the language and your compiler does support it, maybe there would still be reasons to overload both this and the equality operators. Yeah?
If you were to do that, overload spaceship and equals, would you have to write not equal?
If you were to overload spaceship and equals, would you have to write not equals? I mean, bear in mind that we're 2 years away from C+20. I think the answer is yes. If you overloaded equal equal, I would expect you to overload not equal, just in the canonical way.
Because if you write only Spaceship, you don't need to write equal equal or not equal.
Correct. Yes, if you write only Spaceship, the idea is that you don't need to write any of the other operators. They just work. But if you want to get the performance that this is leaving on the table, then you should and could overload selected operators at your choice. OK, so where are we? Yes. So operator Spaceship guidelines then. Obviously, it's too early to adopt it. It's C++20. Library support still being figured out. That it has good promise. You can play with it on godbolt.org, but the implementations aren't quite there yet. For instance, at the moment, you do not get all of the generated operations, as far as I know, in any compiler that's at least live on godbolt.org. And so there are library functions, isEq and isAny, and a few other things in compare that come along to help you get around that a bit. As I said, there are some issues and performance with containers, with generic code, with composition that I think still have to be worked out. So we've got some way to go yet figuring out this operator. It's got a few rough edges. It's very, very new. But I thought it was a good thing to cover. OK, so much for convention and kind of state of the art and all of that. What about if we choose to stray from convention with operators? What could we gain from breaking the mold? So let's have some fun. And this is one of my favorite quotes. Alice in Wonderland and Through Looking Glass is the best book on computer science for the layman, it is said, but that's because it's the best book on anything for the layman. What we get when we break from convention, a lot of the time, is DSLs, either large or small. And why we might want DSLs, domain-specific languages, EDSLs in a sense, I suppose, they're embedded in C++. DSLs are where types and operators work together to make code easier to understand. Especially, they shine where the objects and classes you want to construct aren't difficult to understand or even maybe explain in a sentence, but it's prohibitively wordy in the language to construct them. So what we're trying to achieve with DSLs is readability. Here's an example of a DSL that we have in the language. The curly brace operator. So we have a square bracket operator. We have the paren operator. Everyone's familiar with those. Initializer list is really a DSL for initialization using the curly bracket operator, in a sense. And this is why we want DSLs, because they give us declarative code. They give us easier to read code. We allow the users of our library to form expressions rather than having to sequence all these statements to build up their objects. So that's a sort of an example of a DSL. There's another more overt example of DSL in the standard, and that is Chrono. There's a couple, actually. One is Chrono dates. So this is an example of where an operator interacts with a user-defined literal, a couple of user-defined literals, and to good effect. Because what we're using here is not mathematical convention, but date convention, to have a DSL with one operator and a couple of user-defined literals. And as I was writing this, I realized this is the only possible defense of using the US system for writing dates. It's one character fewer, so I'll give you that. Of course, the bottom one is the correct way. So this is interesting because when we think of DSLs, we might think of, lots of different operators working together. This is a one-operator DSL, but just using one operator even improves readability so much. If you think about what it would take to construct today's date without that slash operator, well, what would you do? You'd probably end up using the plus operator which would work, but it wouldn't be nearly as readable. So this isn't, although this isn't mathematically conventional, we're not dividing these things. This is date-wise conventional. Here's another example of a one-operator DSL that some people on Reddit don't seem to like, but I'm going to speak up in its defense. It's non-conventional, but it works brilliantly. It's taking what we already fundamentally do with strings. We concatenate them, and it's just giving us an easier way to do it. And I've spent far too much of my life checking to see whether strings were terminated with that trailing directory separator. I'm sensing some of you have too. Operator slash just does the right thing. And it doesn't matter whether there's a trailing slash there or not. It will do the right thing. So this is an example of a one-operator DSL, which works brilliantly. So here's an example of a multi-operator DSL. Now, there's a lot going on here. Just take a look at it. This is confusingly, this is called Boost SML. It's actually not a Boost library. I don't think I see Chris in the audience. So there's a lot going on here, but oh, hi Chris. There's a lot going on here, but even if you've never seen this before, I hope that you can see. So this is a very concise definition of a state machine, and this is essentially a declaration of a state machine. It's one return statement here. And what we've got is a series of states on the left. The star marks the starting state. So we're in a state. We get an event with the plus operator. There's possibly a condition or a guard as to what that event has to satisfy with the square brackets. Then there's an action after the slash. And then finally, we may go to a new state. And X is the terminating state. And this follows, not mathematical convention, but this follows some of happily, the UML state spec, I guess state diagrams in UML, use some things which are translatable into C++ operators. So you can look at a piece of code like this, and you can see the flow of the state machine. And what the operators have given you is that concision, that ability to view it all in one place, and to have a chance of understanding it. If this were not using operator overloads, I think it would be very, very difficult to see exactly how the state machine flow happens. Titus.
How critical do you feel the user-defined literals are in this?
How critical do I feel the user-defined literals are? I think they fulfill a really good role. So if they weren't there, they would probably need to be types that I would need to define as, say, tag types somewhere else. And I think I could actually do that. But the usual way to animate this state machine, to make this work, is to use the user-defined literals, the underscore s's. So what that does is turn the string into a type which becomes that state. And I think that's really nice here. So UDLs working in concert with operators works really well, both in the date library and in this case. So, Titus shrugging. I think it's important. I think it's important for readability. Bryce?
How many people have underscore S UDL somewhere in their code base? How many of those are this type? This is concerning.
Yes, Titus is concerned about clashing UDLs. So underscore S is a somewhat popular choice for a user-defined literal, perhaps. This underscore S comes from the Boost SML, the SML namespace. So I've got using namespace SML up there. Okay, so maybe, is there a standing document somewhere that maybe in future will give us guidance on this? Or?
Not on this. I mean,
not on this.
The standard says we get all of the underscored ones.
Right.
It is chaos in the land of single underscore. And we have basically we have created a global flat namespace. So buyer beware.
Good observation.
I mean, it's inside of the namespace, but you can only use it after you've brought that namespace into your
Yeah. The available space of user-defined literals outside of the standard is fairly free-for-all. That's a good observation to make. Lenny?
You can really use any type here, so this is just trying to create a type.
Right, yes. The underscore S here is turning the string into a type to make it that state. Okay, so monads come up a lot lately. We seem to be thinking about monadic things in terms of stood optional, stood expected, stood future. What's the biggest problem with monads? Is it understanding? Is it understanding them? Is it explaining them? Is it category theory? Is it the sudden urge to try to make everything monadic? Well, this is an operator's talk. This is the biggest problem with monads. Haskell's bind operator has the wrong associativity in C++. And the wrong precedence in all probability, yes. In C++, this comes back to what I said at the top of the talk. There aren't that many good choices for operators in C++. So this is what I would like. So let's say this is futures, right? I'm not making any assumptions about how the futures are implemented, just that we would want to compose asynchronous operations monadically in some way. So we've got functions that return futures, and we could chain them together in this way. So we want to call F, with the result of that, split to G1 and G2, bring those back together to call H. We might write that today in some hypothetical futures library as some code that looks something like this. And this would be considered pretty nice today. We've got a future that can split, and we call then on G1 and G2, and then we call when all. These are familiar things to anyone who's attended a talk on futures or read papers or anything like this. And again, this is not really saying anything about how the future is implemented. Hi, Bryce. Now, what I would like to be able to do is something like this. And you can see, I think, when I use operators to compose these, we get that intuition. This is what operators give us. I can rearrange this computation much more easily when I've used operators to put it together in a single expression. So I'm running F, and then I'm going to split G1 and G2 and run those in parallel, and then I'm going to forward that into H. Now, I don't have a good sense of what will become conventional, if anything, in monadic operations and operator overloading. But as far as C++ goes, this is a reasonable way to go, maybe. We might get something like this with continuations, I'm told, with coroutines, sorry. I'm not sure how it's going to go yet. But the point here is that when we use operator overloading, it can clarify the computational structure. It allows me to think about separating my business logic from my strategy of parallelism for this thing. All right, let's go quickly now. So a few mechanics of writing operator overloads, choices, and preferences we could make. One choice is a free function or not a free function. I would say normal rules apply here. Prefer a free function where you can. As I said, they promote encapsulation. They help you to keep the basis functions of your class minimal, complete, and stable. Building convenience functions, in particular with free functions, promotes encapsulation, where you're relying on the class interface and not the class implementation. And free functions have this slightly more nuanced advantage that they put their operands on an equal footing mentally, if you like. And to me, it's more natural to think about it that way, especially if the operation is commutative. Binary operators generally should be implemented in terms of their assignment counterparts. This is part of providing a complete set of operators. When you overload operators, you should always think about providing the complete set so that you do provide your users with that ability to manipulate things and do what they would expect. a curious thing about assignment operators is that the regular assignment operator has to be a member function, but the plus equals, the minus equals, all the other assignment operators don't have to be member functions, and I'm not sure why. Does anyone know why? I'm seeing, oh, Agustin.
The compiler will generate one for you implicitly in certain conditions, so it has to know what it takes.
Right, okay, so the compiler will generate an assignment operator for you. That's why it needs to be a member function. Okay, well, I get the rationale for it being a member function. I'm not sure why the plus equals, and they don't have to be generated, but it seems odd to me that one, because they have to return L value references. They're effectively on the same page, but anyway. So when you're writing operators, of course, they are functions. So everything that applies to normal functions applies to writing operators. Don't forget all the qualifiers. We get a new qualifier every standard with C++. Think about your parameter types. Think about your return types. Hopefully this is all obvious. This entire slide is like one talk in its own right, so I'm not going to dwell too much on it. So let's recap on some operator guidelines. When to use operator overloading, in my opinion. So when you have a natural binary function that combines your types, it's a good choice to think of an operator to do that. When your types obey any kind of mathematical principles that your users will intuit, particularly associativity, and when you want to give them the opportunity to manipulate expressions. When you want to make complex construction of objects easier, and this is where you can combine it with UDLs, and when you want users to intuit properties of your types. So that's when you should use operator overloading. Now, when shouldn't you use them? Well, one important thing I've sort of not quite touched on is, I said when you have a natural binary operation, if that operation could be extended to an n-ary function and you can provide better performance by writing an n-ary function and not forcing your users to combine things with the binary function, that's an important use case to consider, and you shouldn't be constraining your users to only using operators. And the other reason when you shouldn't use operators is just when they aren't ready for prime time yet. So we shouldn't do dogmatic operator overloading. Okay, some don'ts. Don't do that. Really don't do that. Try not to break associativity. Again, most things are associative. Things that aren't associative rapidly become very unusable, really. Don't be afraid to just overload one operator, if it makes sense. We saw some great examples of single operator DSLs. It can really help with readability. Probably still stay away from overloading these operators, even with P0145, even though comparator is now safe to overload. Probably best to, and don't pick weird operators if your type is mathematical. Just try to stick with convention. There's no good convention for the comma operator that I know of. So, do use conventions other than mathematical ones. Do consider this idea of an affine space. So if you look at your types, do consider separating them, and that will help you explore the design space for operators. It's worth trying to separate your types and seeing where it leads. Do use operators, especially if you have non-commutative functions, and that will allow people to leverage fold expressions to put together their objects. And do use user-defined literals as a counterpart to operators to help with construction. And if you provide one operator, think about providing all of the operators that go with it. And with that, I'm about on time, so thank you very much. Hello, Bryce.
You didn't talk about the call operator or the indexing operator.
I didn't. Sorry, what was the first operator?
The call operator.
That's right. I didn't talk about the call operator or the indexing operator.
What are your?
I'm sorry.
What are your thoughts
Was that a
on-
question? That was a comment thinly disguised as a question?
It was a statement. What are your thoughts on those?
What are my
operators?
thoughts on the call
When you should overload them, when you shouldn't? Best practices.
Far too complicated to answer in 3 seconds, which is what I have left. But yeah, I'm happy to talk about operators to anyone that catches me afterwards. It's a complex subject.
Yeah, what's your personal opinion on the ability to add new operators to the language, like an OCaml? Like any token, any sequence of tokens can be a new operator? You think that's
My opinion on adding new operators. C++ has this strange dichotomy between functions and operators, which I don't quite understand, and I would like to be able to unify them. I don't know how realistic that is, really. And what I said at the top of the talk, all those things we can't change are, in theory, ripe for a meta-operators paper from Herb, right? To give us those rules in the language. That's pie in the sky, of course. So, I don't know.
Sorry for the comment, completely undisguised as a question.
Okay.
It's not just aesthetics to provide operators as free functions. The equal footing actually is not just aesthetic. It's the left-hand side is privileged with regards to lookup.
Yes.
If it's a member. So if you want lookup to be symmetric, you have to have it as a free function.
Yes, that's a good comment. Thank you, Gashpa. I assume that was recorded since it was on the mic.
One annoyance thing about providing operators as free functions is when you start doing mixed type comparisons, you suddenly have twice as many or 4 times as many.
Yes. Operators as free functions can lead to combinatorial things. That's true.
Not a question.
Thank you very much.